Welcome everyone back to the second installment of Ceph Tech Talks of 2016. If you missed last month, we had a great one with the folks doing PostgreSQL on Ceph under Mesos with Aurora and Docker. So that was pretty awesome conversation. This month we're having another great one. We're having a CephFS update. This will be the last major kind of CephFS update we see here before the next major release of Joule, which will include CephFS and all the new hotness, moving from the nearly awesome camp into the fully awesome camp. So we're all very excited about that. So without further ado, I will let John give you a rundown of what's new in CephFS and where we're headed. John?
No pressure, huh?
Right.
Okay. So hello, everyone. Thanks for coming. I'm a developer at Red Hat. And I work primarily on the Ceph file system. I will just share my screen so that you can see my slides. While I've got my slides up, I won't be able to see the Blue Jeans chat. So if anyone has any questions, go ahead and ask them there. And maybe, Patrick, if you could just interrupt me verbally if that comes up.
Sure.
So today, I'm going to give a very brief recap of what CephFS is and what its architecture is. But primarily, I want to talk about what's new in the Joule release of CephFS, which is what we've been working on over the past 6 months to a year. So if you're not familiar with Ceph, then you might not fully understand everything here. There are other resources available if you need a from-scratch introduction. I'm hoping that most of the people who are watching this have an existing familiarity. So CephFS, the file system interface to Ceph, is one of 3 application interfaces that you get with the Ceph cluster. Going from left to right, we have the Rados gateway, which provides an S3-compatible object interface to the cluster, RBD, the Rados block device that provides a disk image type access to the cluster, and then CephFS. All of those 3 sit on top of Rados, which is the underlying resilient object store that Ceph is built on. So CephFS is a POSIX file system. What that means is it has a higher level of consistency than a typical NFS or Samba file system would. You get all the same semantics when it comes to locking and concurrency that you would on a local file system like ext4. The data is stored directly in the Rados cluster. So data goes directly from where you've mounted your file system to Rados. It doesn't go through any intermediate servers for the file system. We have a separate metadata server called the Ceph MDS that can act in a cluster to spread the load of the file system metadata across multiple servers and avoid a bottleneck. And we do a little bit more than the average POSIX file system. So in addition to normal file system operations, we have a couple of special additions, which are the ability to take per directory snapshots of the file system and also maintaining recursive statistics. So for example, you can look at the statistics on a directory in your file system and see the total size of files within it without having to run, for example, df to iterate through the file system, which is a comparatively expensive thing to do in a network file system. So in visual form, at the top of the diagram here, we have the CephFS client. You have a choice between a user space client, which uses Fuse, or the client that's built into the Linux kernel. So the upstream Linux kernel includes a CephFS client. And that client, where you've mounted your file system, talks directly to the Rados cluster. It sends the metadata to special metadata servers, which are represented by the little tree icons in this diagram. And it sends the data to OSDs directly. The motivation for CephFS, or distributed file systems in general, is firstly that you have a lot of existing workloads that expect a file system, and those workloads aren't going away. You might have some applications that will use an object store, but you will always, well, for at least for a long time, you'll still have file system workloads. File systems are useful because they're very familiar to everybody. As well as having applications that already depend on them, you also have system administrators who know how to deal with them. And you have other storage systems that know how to interoperate with a file system, such as backup systems. not just legacy systems, but also new systems use file systems. For example, in emerging container environments like Docker, what they call volumes, their units of persistent storage, are themselves file systems. So while we've gone through a sort of region where block devices were the standard way of storing your data in virtualized environments, in containerized environments, we're seeing a return to file systems. And aside from all those compatibility reasons, the features you get with a fully featured file system are actually useful. So being able to set permissions, access control lists, and being able to have a hierarchical way of referring to your data are intrinsically useful concepts for some applications. So the reason we don't use a file system for everything is that they're actually harder in some ways than other ways of accessing storage. Unlike an object store, we're not dealing with a flat representation of the data. And the pieces of data we're storing, the files and the directories, are not independent. They have these relationships to one another that form a hierarchy. And that means that spreading them out across a cluster of servers is a more challenging problem than doing a similar thing with an object store. It's also challenging to deal with some applications. If you've got an application which is written against a local file system, it has expectations about latency and performance that don't really make sense necessarily in a distributed high-scale environment. The classic example is when people like to run ls-l on a directory. It seems like a very innocuous operation, but on a distributed network file system, you're potentially issuing a very large number of metadata IOs in order to retrieve all of that metadata for the to know what color the files should be in your terminal when you run ls-l. The concurrency in a distributed file system is also more complex than in other forms of storage. When you've got multiple file system mounts coming from different hosts, if one client is opening a file and writing to it, and another client would like to open it and maybe read from it at the same time, in order to enforce our POSIX semantics, there's a fair amount of complexity that has to exist within the metadata server and within the client in order to make that happen. So those are the downsides to a file system. Why is it hard? Why is it taking such a long time for this and other distributed file systems to reach a level of maturity where you would use them alongside your object and block interfaces? To give a more concrete illustration of what CephFS is and how you use it, here are paraphrased the commands that you use if you have an existing Rados cluster and you want to start running CephFS. So the Ceph deploy tool knows how to set up a metadata server. So you'll need one of those. For a CephFS file system, you need a data pool and a metadata pool. So you create two Rados pools. And finally, there is a command called CephFS new, which configures the file system and tells the Ceph cluster which pools you would like to use for it. Once you've created your file system and your metadata server is up and running, you can start using your file system by mounting it from a client. The example at the bottom there is how you mount a Ceph file system using the kernel client, which is part of the upstream kernel. The command line that you would use for using our user space Fuse client is a little different, but it's the same workflow. So that was your lightning tour of CephFS and what it is. And I'm now going to step through all of the new stuff. So the biggest thing, and the thing that I think a lot of people have been waiting for, is the ability to scrub the file system for errors and repair it when something goes wrong. This kind of functionality is critical to moving CephFS into a production-ready state, because it means that not only have we stabilized the software somewhat and removed a lot of bugs, we're now in a position where even if we do encounter bugs or unexpected issues, we have the tools that we need to detect issues and correct them on a customer system. In general, the resilience and self-repair of the data and metadata that's stored in CephFS is actually the underlying Rados cluster's job. So when CephFS writes some inodes or some file data into Rados, it's getting replicated, and when one of those copies, when one of those disks dies, it's Rados's job to deal with that. So the scrub and repair stuff in CephFS isn't about the everyday data resilience, because that's already taken care of. It's about disasters. It's about the unforeseen. Serious software bugs, which clearly we go to great lengths to avoid, but are possible. Or scenarios where Rados can't do its job anymore. For example, if a user only has 3 copies of their data and they lose 3 disks due to some severe bad luck or some configuration error, we would like it to be the case that rather than entirely losing access to their Ceph file system, as has been the case in the past, they're able to selectively identify and repair the damage done by that data loss in the lower layers. So in the dual release, we now have that capability for many forms of metadata damage, principally the loss of objects, which is the kind of scenario that you would see if you had a triple failure of disks in RAIDOS and you'd lost a certain number of your placement groups, but also for corruptions, which we don't generally expect to see in a RAIDOS cluster, but that's really more of a proxy for what would happen if we encountered some unexpected software bug. If we encountered some structure on disk which just didn't make sense or we couldn't decode it, that would be a corruption. These tools are for use in disasters and they require expertise. They're primarily intended for vendors providing support for CephFS to be able to intervene in extreme situations and repair the systems. They are not something that ordinary users would be using every single day. So to go into more detail about what the new scrub repair stuff looks like. Historically, if CephFS encountered something it didn't like on the RAIDOS cluster, a couple of versions ago, the metadata server would generally assert out, which clearly looks like a crash to the user and essentially is a slightly safer form of crash. In the last release of Ceph, we added the ability to mark MDS ranks, which are the roles in a cluster that's occupied by an MDS daemon, as damaged, so that when they encountered something that they couldn't handle on disk, rather than crashing, they would report that and go into an official damaged state and wait for intervention to fix them. In Dual, we're more fine-grained than that again. So when something bad is found within the RAIDOS cluster, the metadata server will be able to identify where in the metadata tree it hit an issue. For example, if a particular directory has damaged metadata on disk, and mark that directory as damaged. Meanwhile, the MDS daemon will stay up. Users will continue to be able to access the rest of their data. And if they try and access that particular broken part, they'll get an appropriate EIO code from their clients. There are some tools server-side for dealing with this situation. So there's a new damage ls command, which 99.9% of the time will give you 0 entries. But if something has gone seriously wrong, it will allow you to see exactly where in the metadata tree you've got issues. There's a corresponding damage rm command, which is for removing entries from that list if you know that you've fixed something using the repair tools. And the third command there is for the situations where we have a non-localized form of damage. If something is wrong with an entire MDS rank, so for example, if some critical data structure has been, critical global data structure has been damaged, that will be reported in the health status, and there is this repaired command for telling Ceph that you have done some intervention in the background and that it should now start using that rank again. So the types of repairs that we can do, if we see inconsistent statistics in the system, we can repair that online. So that's a process by which the MDS daemon will traverse a tree of metadata and work out things like what should be the file count for a directory, or how many children should a directory have recursively. Currently, all the other repairs, such as if we have orphaned files, they happen offline, which means you need to stop the MDS and go and fix them in the background. So the online capability that we have here, I'll come to the offline in a second. Firstly, we can scrub a particular path. So that path that the user passes in will be a file or a directory, and the MDS will go and check what's on disk versus what it has in cache. And if there is nothing in cache, it will just check that it can load it from disk. And it'll tell you if everything's okay, if what's on disk seems to be healthy. Secondly, there is a recursive flag for that, which will do the same thing, but will go all the way down into a directory. Thirdly, you can pass a repair flag to it, which will go through this procedure, but in the process, if it finds any statistics that it doesn't like, it'll rewrite them. That's the online repair capability that I mentioned a second ago. And fourthly, there is a command called tag path. And what that does is similar to a scrub, but instead of going through and just checking all the metadata, It also goes and updates the data pool where the file content is stored and tags each file, the first object in each file in the data pool, to indicate that it was found while traversing the metadata. That enables you later, using the tools that I'll come on to next, to iterate over the data objects and identify which of those are not hooked into the metadata tree and might need reinserting if you have an orphaned file. So the scrub commands will give you a message when they complete. They'll actually give you a little JSON structure that will tell you about what, if any, issue they found. And they'll also emit cluster log messages. So if you're not around to see the result of the command, if you have a long-running command, you'll also be able to see in the cluster log if they found any issues. So that process of iterating over the metadata is what we call a forward scrub. The backward scrub is where we iterate over all the data objects. So that number of objects is of the order the amount of data in your system. So your data files are stored chunked into 4 megabyte objects. And depending on how many files and how big they are, that will influence how many data objects you have. So you're iterating over all of them, which is, hopefully you can see that that means this is an unusual thing to do. You don't want to do this continuously. It's not a particularly fast thing to do, and you really would only do it in a disaster to find any orphaned files or recover any invalid file size information by searching all the objects. It's an exhaustive search of the data objects. In order to mitigate the fact that it's an exhaustive search, we've added the ability to run the workers in parallel, and I'll show you what that looks like on the next slide. So the backward scrub process is done using the CephFS data scan tool, and it's a two-step thing. First, the scan extents command lets us iterate over all the objects in all the files. So once we've seen all the objects in a file, we can work out how big it is. So then that's the first step. We've worked out how big all the files are. Then the second step is where we iterate over just the first object of every file. And we have a new little bit of code on the OSD side, which lets us efficiently iterate over just the first objects in the files. And for each of them, go and find it in the metadata. And if it wasn't already linked in, we can go and modify the contents of the metadata pool to create a link to this file. In general, we can recover file names because CephFS stores something called a backtrace on data objects. That's not guaranteed to be there, and if it isn't, then we will inject lost files in a lost and found directory. So just the same as if you ran FSCK on an ext4 file system, you would potentially see things getting linked into the lost and found folder. We now have that concept in CephFS as well. To make this more efficient and avoid iterating over absolutely every object, you can run the tag path command that I showed on the previous slide. So these operate in concert. Tag path lets you identify which files are already linked into the metadata tree, and these exhaustive scan commands will let you iterate over just the objects that weren't tagged in order to somewhat more efficiently recover any lost files. In order to enable doing this in parallel, we have some new functionality in Rados, which allows us to iterate over just a subset of the objects in a pool. We don't currently have a very user-friendly way of running this. If you want to run a large number of workers in parallel, it's up to you to orchestrate running them across a collection of clients. You probably would want to write a shell script of some kind to do this. Each individual worker, though, is fairly simple to invoke. There's just a -- worker n and -- worker m argument. So you tell it, I want to be worker 3 of 10. And you start 10 processes like that with a different value of n for each one, and you'll be able to do a 10-way parallelism, for example. Just to reiterate, this is disaster recovery functionality. Don't go running all of these repair commands just in case they fix something, because it is possible for them to make things worse as well as better. They are invasive things designed to operate on an offline cluster. There's also some future work to be done here. The forward scrub functionality needs to be more multi-MDS aware. So currently we're sending these commands directly to a single MDS and operating on whatever happens to be in the cache of that, in the metadata that allocated to that MDS at one time. It doesn't handle distributing this across multiple daemons in a multi-MDS situation. And we're also not currently running this in the background opportunistically the way that we do with Rados scrubs. So at some point, it would be nice to extend this to schedule file system scrubs to happen in the background the same way we do with Rados. So that's it for scrub and repair, and I'll move on to the next topic. But before I do that, I just wanted to drop out of the presentation to check that the video conference was all still connected and that kind of thing. It seems to be, so that's great. So the next thing I want to talk about is improvements to authorization in CephFS. The clients in a CephFS file system, the servers that are mounting it, need to talk to the Ceph monitors, the Ceph OSDs to store their data, and the Ceph MDS daemons to do their metadata operations. We already had the ability to limit how clients could talk to OSDs. So we could tell them they could only talk to a particular data pool, and then we could create layouts in CephFS for files and directories that put the data in particular directories in particular data pools, so that you could have some level of separation between what clients could see and which clients could touch each other's data. Historically, you didn't have any finer grained control over which parts of the metadata the clients could see. So that's been fixed now. There's now an extension to the auth caps, the authorization capabilities that we use for authorization within Ceph, so that when we give clients the capability to talk to an MDS, we can be more specific and say they have the right to talk to MDSs, but only within a certain path or only using a certain UID. What that looks like is shown here in this example. So the typical use case for this is that we have a client and we want that client to only be able to see data within a particular pool and only be able to see metadata within a particular directory. So if we have a directory fooder and we have a pool foo pool, and we've linked those two up by setting a Ceph layout, a Ceph file system layout on fooder that points it to foo pool, we can then craft one of these authorization caps for a client that tells it MDS allow RW path equals fooder to limit it to that. And the existing ability is still there to restrict which OSDs it can talk to as well. And the new part is what's in bold then. Once you have a client that has capabilities like this, it needs to be started in a certain way in order to work. So because it can no longer see the root of the file system, it can only see this directory, you need to pass the -r flag, which tells the client which directory to treat as its root. And it needs to have a root that it is actually permitted to read. Once you've gone through this setup, you effectively have a client which can only access one part of your file system, and as far as that client is concerned, that is the root of the file system. Next up, on a similar theme, I want to talk about improvements to file layouts, so that in addition to having a file or directory layout that points files to a particular pool, we're going to be able to point files into a particular Rados namespace. So you may not be familiar with Rados namespaces. They are a cheaper way than pools to subdivide your cluster. So pools involve creating PGs, and PGs consume CPU and RAM. And when all we want is a logical separation between one set of objects and another set of objects, we would like a lighter way of doing that. And that's something that's existed in Rados for quite some time. It's called a namespace. And they're implemented effectively as just a prefix to object names. So they create a different logical namespace as opposed to a pool, which is going to physically store the data and handle it separately. So there's an existing ability to write OSD auth caps that limit you to a namespace. So if we could write our files to different namespaces for different Ceph clients, then this would be a good way of providing security that prevented two clients from seeing each other's files without the overhead of creating whole different pools. So that's what has been done. The existing layout fields, you had the ability to set a pool and then the ability to configure how the object was going to be striped with stripe unit, stripe count, and object size. So there's now just an additional field there called pool namespace. There's a caveat here, which is that on the client side, all of the information for a file that it needs to access, the data itself, is going to go into that namespace. But we do also store these backtraces, which are an implementation detail of CephFS, from the MDS for each file. And as was the case with customizing the pool that's used for a file, we will write the backtraces from the MDS still to the default pool and the default namespace. I don't really have time to go into why that is, but it's something to be aware of, that what you'll get is your file data in the namespace that you've asked for, and that's all the client needs to see. But the MDS that's dealing with this metadata will still need to be able to have access to the default namespace in order that it can write the backtraces there. Those two features are actually somewhat motivated by what I'm going to talk about now, which is OpenStack Manila. So OpenStack is the open source cloud framework for building private or public clouds. It has a number of different services that make it up. So Nova, the compute service, Cinder, the block storage service, Neutron, the networking service. And one of those services that was added a little bit more recently than the better known ones is Manila, which is a service for provisioning and accessing shared file systems as part of your cloud. Manila provides a model to users where it allows them to request a piece of file system storage that it calls a share. And Manila has a plugin framework that enables you to write drivers for it. So for example, there is a HDFS driver, there is a GlusterFS driver, and there are drivers for integrating this with various proprietary storage appliances as well. So we've gone ahead and written a CephFS driver for this. And in CephFS, the way we implement the Manila concept of a share is actually just as a directory. We're able to do that because the type of operation that Manila likes to do on shares, things like snapshots, are actually supported in CephFS at a per directory granularity. So Manila expects us to be able to limit the size of shares, and because we're just using directories, there actually is no such limitation intrinsic to the way we're doing it. We add that on by setting quotas. So that's a little bit artificial, but it gives the user the behavior that they expect. Similarly to what I was talking about with MDS auth caps that limited access by path, the -r flag is needed by the client. So when we've created a share for a user, we give them their path as something like /manila/ a long alphanumeric ID, and they need to pass that into the -r flag to their Fuse client in order to be able to mount that share. We take advantage of the recursive statistics feature of CephFS in order to get the capacity statistics. So when we're reporting to Manila that a given share is using a certain number of bytes, because a share is just a directory, where we're getting that data from is the rstats within CephFS. And using these new auth caps, we're able to make sure that clients only have permission to access the particular directory which corresponds to a share that they have been explicitly granted access to. That's very important because an OpenStack cloud is a multi-tenanted environment. So Manila really represents a use case that brings together a number of these different features that we've been working on recently, as well as a number of useful features that have existed in CephFS for some time. And it wraps them up in a way that makes the whole thing a lot more accessible to users. So they don't have to type those long ceph auth get or create commands anymore. That's now being done inside Manila on their behalf. Just to go into a little bit about where the code lives for this. So in order to enable the Manila driver, there is a new Python interface in the Ceph tree. So alongside where we have the Python bindings for things like Rados and libCephFS, we now have something called CephFS Volume Client, which is a descriptive, if not elegant name. And that is what our CephFS driver in Manila talks to. So within the Manila tree, we've got Manila itself and then the CephFS driver. And then within the Ceph tree, we've got CephFS Volume Client, and that wraps up all of the operations that are done through librados and libCephFS in order to, behind the scenes, create these directories, set the right layouts on them, set the right auth caps for accessing them, and then hand up to Manila this abstract volume concept, which happens to be implemented as a directory with a bunch of magic auth caps on it. So we're working to get this driver included in the forthcoming Mitaka release of OpenStack, and we'll be talking about this and other future Manila-related CephFS work at the summit in Austin this spring. The last thing I want to talk about is a new experimental feature, which we're hoping to get into Dual. So historically, one Ceph cluster meant one Ceph file system. There is no actual fundamental reason for that. It's sort of a convenience of implementation thing. But there are good reasons you might want to have multiple file systems, which means having multiple MDS clusters that are all sharing one Rados cluster. So if you want two separate Ceph file systems, rather than having to have two Ceph clusters, you can now back it all onto the same Rados cluster. You might want to do this, have multiple file systems, if you want to physically isolate some workloads. So if you want to make sure for security or quality of service reasons that two different workloads, maybe one is very mission critical and one is experimental, are just going to go through physically separate MDS servers, you'd be able to do that. There's also a disaster recovery use case, which is quite a strong motivator for us here, that currently, if you're going through some of the repair procedures that I was talking about earlier, you're kind of trying to do a lot of stuff in place, and that's kind of a scary, uncomfortable thing to do. So once we have the ability to have multiple file systems in a system, in a single Ceph cluster, I should say, we'll be able to have a workflow for disaster recovery where someone creates a new file system within the same cluster and then does disaster recovery operations that are scraping what they can recover from their old, potentially broken file system into their new file system without having to throw away or modify the file system that you're trying to recover from at the same time as you're writing the new stuff. And finally, there's a general resilience argument for this. So if you're worried about hitting issues, whether they're bugs or performance issues or stability issues in CephFS, then it's a nice way of protecting yourself if you can say, well, I've got a stable workload that's working really well. I'm going to keep that running on this MDS in this file system. And then when I want to try doing something different, I'm going to run that on a different MDS with a different file system so that the one thing doesn't interfere with the other. So the fsnew command that I mentioned at the beginning, that's something that was added a little while ago. The fsnew, fsls, and fsrm commands, which very much suggest you should be able to have more than one, but historically would give you an error if you tried to create a second one. Well, now you can run it more than once. So you run fsnew a second time, and you give it a different couple of pools to use, and you'll get a second file system. Hopefully before doing that, you have created enough MDS daemons to actually operate the new file system. So if you only had one MDS daemon and you had one file system and then you create a second file system, well, the second file system is not going to be able to come up yet. In this initial implementation, the MDS daemons are all treated equally. So if you have two file systems and one daemon, there's no promise about which file system is going to come up. It's just going to allocate the daemons on a first-come, first-served basis to file systems that would like a daemon. That's something that we can improve on in the future. But for the moment, as long as you've got at least one more MDS daemon than you have file systems, then what you'll have is a standby MDS daemon that will step in and help with whichever file system loses a daemon. So the standby will be available to participate in any of the file systems. You just don't have the ability to say which at the moment. This is switched off by default because it's brand new and experimental. So much like snapshots and inline data, we have a flag on the cluster that you have to explicitly set to indicate that you are aware of the caveats and that you're not going to get angry with us if something goes wrong. For legacy clients, which don't support explicitly selecting which file system you'd like to connect to, we have an ability to configure which the default file system should be. So if you create 3 file systems and you want the second of those to be the one that old clients will get when they try and connect to the system, you can do that. Whereas if you're using the new client, or I should say the latest version of the Fuse client, you can pass an option on the command line to say which file system you want to use. If you omit that option, then like a legacy client, you will get the default file system. So if you're not actively trying to use this, if you just have one file system, everything will just still work the same on the client side and on the server side. You won't know the difference unless you've set this flag and created a second file system. So there's a bunch of follow-on work to improve this. Much like with data storage, it would be nice to be able to use Rados namespaces for metadata storage as well, so that if I'm creating a second file system, I don't have to needlessly create a second metadata pool. I could just use a different namespace within my existing metadata pool. There's a bunch of authorization work needed here to make it suitable for a lot of use cases, especially multi-tenant use cases. So currently, there's nothing to limit a client to connecting to particular file systems. So any client can connect to any file system, and any MDS can act as a server for any file system. The file system selection stuff doesn't exist in the kernel client yet. So currently, the ability to pick on a client-by-client basis which file system you get is limited to the user space client. And as I was mentioning, the MDSs are all considered equal, and you can't currently set up any clever policies that say this MDS is for that file system and that MDS is for the other file system. But I'm personally quite excited by this feature because it's been a sort of annoying limitation for quite a while, and we're getting rid of it. So I'm going to wrap up with some tips for anyone who is thinking of or already is an early adopter of CephFS. This is a stock slide that I put in a number of presentations. So come to the mailing list, come and look at the issue tracker, look at the online reference for how to configure logging and debugging so that you can get more information about any issues you're having. And then when you are having an issue, please consider installing the most recent development release, or if you're using the kernel client, a more recent kernel, because CephFS is very actively developed and there's a lot of difference between the code from 6 months ago and the code from today. If you're getting in touch with us, please let us know as much detail as you can. How are your MDSs configured? How many of them have you got? Which client are you using? Is it the kernel? Is it user space? And so on. And what are you doing with the file system? So there's a big difference for a distributed file system between a workload where you've got just a single client versus where you've got multiple clients accessing the same files and so on. So really just as much information as you can gather using the tools, and then as much information as you can give us when you're reporting issues is really helpful. And we really appreciate the feedback when we can get it. Okay, so that's all I've got, and I'll drop out of the slides and we'll see if there are any questions at all. Questions don't have to be about the new stuff in here. If anyone has any general CephFS questions, that's fine too.
Awesome. Thank you, John. That was great. Oh, looks like we have a question already from Daryl. It says, what is the timeline for when CephFS is generally considered production ready? And what about the production readiness of features like snapshots?
Okay, yes. I should have mentioned that. So the dual release of Ceph, which is the release happening this spring, is going to be the first one where we're going to start calling the upstream open source release stable. And we're going to be encouraging people to start evaluating it, start testing it. As for official supported releases of products based on this code, whether it's by Red Hat or any other vendors, that's TBA. But yeah, Joule is the stable release of CephFS. You've also asked about snapshots. Snapshots are not, I think currently we're not including that in our sort of statement of stability for Joule, but there has been recent work on stabilizing snapshots, so they're coming along as well. So I'm being vague about everything apart from Joule and the statement that Joule is going to be Joule is going to be the upstream release of CephFS that folks should start testing and evaluating and complaining to us about bugs with.
Yeah, Daryl, to expand on that a little bit, typically what you see when an open source version of Ceph is released and is stable and whatnot, typically it's about a 6-month window to when the Red Hat supported packages come out that include those things. Modulo any problems, concerns, things that they want to expand on before putting it in the Red Hat Ceph storage product, that kind of thing. So the commercially supportable is typically about 6 months behind. So, all right. The next question is from Logan. What's the relationship between file and object? You want to expound a little bit about how the object mapping and placement groups and stuff work with respect specifically to CephFS?
Okay, so there's 2 questions you might be asking there when you say what's the relation between file and object. You might be asking what's the relationship between files in CephFS and objects in RGW, and the answer to that is there is no relation. They're separate. So they're both using the same Rados cluster, but the data in a file and the data in an RGW object, the 2 things cannot see each other. As for the other interpretation of the question, which is how are the files in CephFS mapped to objects in Rados, they are striped in the same way that they are in RBD or RGW. So you can configure that with the settings on a file layout. But the default, which most people, I think, go ahead and use, is to simply stripe chunk objects into 4 megabyte chunks. So if you write a 4 megabyte object, that's going to be, if you write a 4 megabyte file, that's going to be 1 object. And if you write an 8 megabyte file, that's going to be 2 objects. There is a little bit of overhead that goes with that. In the cases where you're storing files in non-default pools or namespaces, you will get the data objects for the file, which will follow those rules about 4 megabyte chunking. And then you will get an additional very small object for each file as well, which tracks some other metadata about it. You also ask if active-active MDSs will be supported. The short answer is no. In the Joule release, where all of the work that we've done on stabilization and repair and so on has focused on the single active MDS case. So the case we're encouraging people to evaluate is one active MDS and then a standby or a standby replay MDS. So standby replay is in general a pretty good idea to get a fast failover. That's the mode where the standby continuously replays the journal of the active MDS. However, having multiple active MDSs, the code is all in there. You can install it and enable it, and you will, in general, find that it works. But that is not something that we've focused on stabilizing. So if you're putting things in a more production ready and less production ready bucket, then active-active goes in the less production ready bucket. We have a question. What about quota in the kernel client? Is it ready? Good question. I don't think we've done that work yet. So I think that's a no. But don't.
Last I heard, the Joule release was still looking at quotas, but that was on the will probably slip to next version list. So my guess is quotas won't make the Joule release.
Mm-hmm. So, Patrick, you mean specifically the kernel client?
Yes, kernel client quotas. Yeah.
How is active passive HA among the MDS nodes handled? Is the standby MDS hot, or does failover need to be handled externally with something like pacemaker? It is hot. So there is no pacemaker in this. The way this works is you start as many MDS daemons as you like. They all communicate with the Ceph monitor cluster, and they essentially register themselves in a list of eligible standbys. And then the Ceph monitor cluster looks at your configuration for how many active daemons you want for any given file system and promotes one or more of the standby nodes to take on what we call a rank, which is a sort of active operating role within an MDS cluster. So none of that requires any external input unless you want to preempt it to get past a timeout. So by default, if an MDS just falls off the network, we'll wait 30 seconds for it before promoting another guy in its place. So you can preempt that using the Ceph MDS fail command. But aside from that, it's an entirely autonomous thing. If you wanted to, I mentioned a moment ago about standby replay mode. So if you want to have a little bit more of a crafted configuration rather than just creating a bunch of MDS daemons, you can, for example, create one MDS daemon with an entry in its ceph.conf file that instructs the Ceph monitors to use this daemon as the replacement for a specific other daemon. And you can also set a flag which causes that standby daemon to continuously replay the metadata log, the metadata journal, from the guy who it is the potential replacement for, which means that at the point that it is asked to take on that role as the replacement, it already has the metadata in cache, and it doesn't have to reload all of the metadata from Rados, and that gives you a faster failover at the cost of some extra read IOs for it following the journal and at the cost of it being a slightly more handcrafted configuration. Okay, would it be a bad idea to try and run the MDS daemons on the same hosts as the Mon daemons? Not necessarily, but in general, they have different requirements. So MDS daemons benefit from having lots and lots of RAM, whereas the MDS daemons don't do any local I/O at all because all of their persistence goes to the Rados cluster. Whereas monitor daemons benefit from having a fast local storage device for storing all of the map data and so on. So in general, what makes a good Mon server doesn't necessarily, hardware-wise, doesn't necessarily make a good MDS server. Aside from that, you just have all of the general issues associated with mixing different daemons on the same server. So we often get asked, can we run Mons and OSDs on the same server? And so there's a similar kind of set of issues that you need to work through if you're thinking about doing that. But in future, we're looking at things like C groups configurations that will enable people to run Mons and OSDs in the same place, and that same kind of work would at some point also apply to running MDS daemons in the same place as Mons. So the answer isn't no, you can run them on the same servers. It's not necessarily a bad idea, but you have to really think through that configuration. Brian asks, how can you scale CephFS to meet demands of a growing OpenStack cluster if you're using it for Manila? So essentially in the same way as we would for any other large workload. So CephFS, 10 years ago, long before I worked on it, the CephFS architecture was originally designed to deal with HPC clusters, which would have very large numbers of clients. And so in Manila, where we potentially also have very large numbers of clients talking to lots of different directories which are acting as Manila shares, it's a similar use case to when it comes to scaling. And so it's the same answers. It scales by increasing the number of MDSs in a cluster, although currently that multiple active MDS functionality isn't stabilized. The other aspect to scaling with Manila is we might also look at integrating the multi-file system functionality with Manila, so that in cases where people knew that they had, for example, one tenant was going to use this set of file systems and another tenant was going to use another set of file systems, you might consider crafting a configuration where you had an MDS for this tenant's file systems and an MDS for this other tenant's file systems, rather than having a completely elastic cluster of MDSs. So it's a mixture of the elastic scaling with the size of the MDS cluster, and then maybe a little bit of manually configured magic for deploying more individual daemons that might operate as part of separate clusters. But the Manila stuff is really very new at the moment, so it'll be interesting to see how that pans out.
Are there any other questions? Now is the time. All right, looks like we don't have any more questions. That was great work. Thank you, John, very much. Just a reminder to everybody here, this was recorded and will be posted up on the YouTube channel, which is also going to be linked from the Ceph Tech Talks site on ceph.com. So if you want to replay or revisit this, it will be there. Otherwise, stay tuned for our next one, which is on 24th of March, same time, same bat channel. So we'll hopefully see you all back then.